There is a volcano in the central Bismarck Sea, 1,300 meters below the surface of the ocean, that nobody knew existed until 1972. It was discovered then because of an acoustic signal that propagated across the western Pacific from its first and only catalogued eruption. After that, it went quiet. For 54 years, nobody monitored it. Nobody mapped it properly. Nobody studied it. Tonight, that volcano is erupting again. A magnitude 5.6 earthquake on the 8th of May opened a vent in the seafloor, and an ash column is now climbing through nearly a mile of seawater and rising another 9,000 feet into the atmosphere. 200 kilometers south, at the bottom of the same sea, lies the debris fan of a volcano that collapsed in 1888 and killed several hundred people. The question we are answering tonight is whether we are watching the same kind of story open again. Quick note before we dive in. If you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs. Let me know in the comments where you're tuning in from. Now let's get into it. Part 1. The Eruption. Somewhere between the islands of New Britain and Manus in the central Bismarck Sea, north of Papua New Guinea, the seafloor has split open. Not on land, not on the surface, down. 1,300 meters down. About 4,300 feet under the surface of the ocean, in a stretch of water that almost nobody has reason to look at, a submarine volcano that has not erupted in 54 years has begun erupting again. And it is not a small event. It is sending an ash column up through nearly a mile of seawater, breaking the surface and rising another 9,000 feet into the atmosphere. Tonight, that plume is still climbing. The earthquakes are still rolling through, and the system that did this in 1888 killed several hundred people on the coastlines around it. The eruption began on the 8th of May 2026, in the early hours Universal Time. It began the way these things almost always begin, with a magnitude 5.6 earthquake at 12:22 UTC, a single, sharp signal, a magma intrusion, large enough to break the rock above it, large enough to register on the global seismic network as the kind of event you do not get without a serious volume of new material pushing up through the crust. Then a magnitude 5.0. Then a string of magnitude 4s, the kind of aftershocks you get in clusters when a volcanic system is opening a new vent. By the morning of the 8th, the satellite imagery showed something that was not there the day before, an ash plume, drifting north, spreading out, visible from a geostationary platform 22,000 miles overhead. This is what we are looking at right now. A volcano that is not on most lists. A volcano with one historic eruption on its record, back in January of 1972, which is also how we discovered it in the first place. The acoustic signal of that eruption was detected, traced, mapped to a location nobody had been watching, and added to a catalogue that nobody really maintained. 54 years passed, and then the seafloor opened again, and the ash column climbed back into the sky. And nobody on the planet has eyes on it directly, because there is nothing to see at the surface, only the plume, only the spreading ring of disturbance, only the chain of small earthquakes that are still rolling through the system as you watch this video. The numbers on this are not abstract. The vent is at 1,300 meters depth. At that depth, the hydrostatic pressure is about 130 atmospheres, 1,915 pounds per square inch, the weight of a mile of seawater bearing down on whatever is happening at the vent, and yet the ash is reaching 9,000 feet above the sea surface. So the total column from the vent floor to the top of the plume is roughly 4 kilometers, 4,000 meters of energy and material moving upward against the pressure of a mile of ocean and then through a kilometer of atmosphere. That is not a quiet eruption. That is not a slow bleed of pillow lavas onto the seafloor. That is sustained, energetic, atmospherically significant volcanism. And the question that is sitting underneath all of this, the one nobody can fully answer right now, is what happens next. Because the volcano this is happening at, the central Bismarck Sea volcano, sits in a volcanic arc with a history. The southern part of that arc, about 200 kilometers to the south, contains an island called Ritter, and in March of 1888, Ritter Island collapsed into the sea. Half of the island, gone in minutes, several cubic kilometers of rock and ash and earth sliding off the volcanic edifice at 40 meters per second, displacing an ocean's worth of water, generating tsunamis with run-up heights of 15 to 50 meters on the islands within sight. Several hundred people died on the coastlines around it. The damage was documented as far as 600 kilometers away. That is the same volcanic arc, the same kind of system, the same kind of failure mode is on the table right now for the volcano that just woke up. And before we go any further into all of this, you should know two things. The first is that the tsunami risk, as of right now, is not active. The Pacific Tsunami Warning Center has not issued a warning. Coastal tide gauges have not registered an unusual wave. The eruption is happening, but the catastrophic downstream event that you would worry about, the flank collapse that could send a wall of water across the Western Pacific, has not occurred. The second thing you should know is that the conditions under which a flank collapse becomes more likely than baseline are stacking. The eruption is sustained. The earthquake swarm is ongoing. The volcanic ridge geometry under the vent is poorly mapped, but appears to extend across tens of kilometers. The system is feeding one visible vent, but the seismic energy is spread across an area suggesting multiple potential failure points. Every single one of those facts is consistent with a system that could fail, in a way comparable to Ritter. And every one of them is also consistent with a system that will simply erupt at its current scale for a few more weeks and then go quiet again for another 54 years or another 500. The honest answer about what comes next is that nobody knows. The instrumentation to know does not exist for this volcano. What this video is about is everything we do know. The eruption itself, the earthquake swarm that opened it, the volcano that we barely understand, the arc it sits inside, and the history of that arc, the 1888 Ritter Island collapse and what it tells us about what the worst case looks like, the other tsunamis this region has produced, the way these systems fail, the way the warning systems that protect coastal populations are not actually designed to detect the kind of event we would worry about here, the cluster of other volcanoes that are doing notable things across the Western Pacific at the exact same moment. The largest volcanic eruption of the 21st century, Hunga Tonga, 4 years ago, and what its pre-climax phase looked like and how it compares to the system you're watching tonight. And the part of all of this that nobody is talking about yet, the question of whether the simultaneous activity across the entire Western Pacific is coincidence, or whether something larger is going on with the Pacific plate. By the end of this video, you will know what the operational risk envelope is. You will know what to watch for in the next 48 hours, the next week, the next several weeks. You will know which of the conspiracy frames you're encountering online are physically impossible at the energy scales involved, and which represent genuinely open questions. You will know what the most defensible interpretation of the event is, separately from the worst-case ceiling. And you will know why the central Bismarck Sea volcano, a system most people had never heard of before this week, has just become one of the most important things to be watching across the entire Western Pacific Basin. But first, we have to go down to the seafloor, down to 1,300 meters, down to where the vent is opening, down to the swarm that started all of this. Because the M5.6 earthquake at 12:22 UTC on May 8th is the door into everything that comes after. Part 2. The Swarm. A magnitude 5.6 earthquake is not, by global standards, a large event. The Earth produces dozens of magnitude 5+ events every week. Most of them happen along subduction zone interfaces or in continental rifts, and most of them are released as cleanly as the rock under stress will let them go. They register on seismographs around the world, they get a catalogue entry, they get an automated alert if they meet a threshold, and then, for the most part, they are filed away. What makes the central Bismarck Sea magnitude 5.6 different is the geology under it. This was not a clean strike slip event on a continental fault. This was not a subduction zone slip releasing accumulated stress between two converging plates. This was a magmatic intrusion. The seismic signature, the depth assignment, the location relative to the volcanic ridge beneath the Bismarck Sea, the timing of what followed, all of it points to a fresh injection of magma into the crust at sufficient pressure to fracture rock and open pathways toward the surface. The earthquake was not the event. The earthquake was the door opening. The event is what came through it. The May 8th swarm began with that main shock at 12:22 Universal Time. Within the next several hours, a magnitude 5.0 event followed, along with multiple magnitude 4 class aftershocks. The latest catalogued event in the immediate sequence, as of the recording of this video, occurred on May 9th at around 0900 UTC, magnitude approximately 5. All of these are catalogued at 10 kilometers depth, which is the standard placeholder value that USGS and other agencies assign when the actual depth cannot be reliably calculated because of sparse instrumentation in the region. The Bismarck Sea is not blanketed in seismographs. There are no permanent ocean bottom sensors in the immediate area. The depth values are approximations. The magnitudes are calibrated against distant stations. We're working with a partial picture, and the partial picture still says this was a major magmatic intrusion. There is also one other thing to understand about the magnitudes here. The global seismic network reliably catalogues earthquakes down to about magnitude 4.5. Below that, in remote regions like the central Bismarck Sea, smaller events are not consistently recorded. There is no real local network to pick up the magnitude 3s and the magnitude 2s, so when you see a few magnitude 5s and a few magnitude 4s in the catalogue, what you should understand is that those are the largest events in what is almost certainly a swarm of hundreds of smaller events that the network simply did not capture. The actual seismic activity in the central Bismarck Sea over the past 5 days is much greater than the catalogue shows. We are seeing the tip of the swarm, not the swarm itself, and then there is the spatial geometry of the swarm, which is the part that should make you sit up. The catalogued events are not concentrated at a single point. They are spread across an area approximately 12 to 15 kilometers across at the inner cluster, with some events appearing as far as 30 kilometers from the primary vent. That is not how a single point source volcano produces aftershocks. That is how a volcanic field produces aftershocks. The earthquake pattern is tracing out a volcanic ridge, a fissure system, something larger than one eruptive center. The single visible vent that is producing the ash plume right now may be the most active point along the ridge, but it is almost certainly not the only point capable of producing eruption. And if the magma supply propagates along the ridge, as fissure systems in places like Iceland and the East African Rift have repeatedly demonstrated, new vents could open in the coming days or weeks. We do not know how big this field is. We know it is bigger than one vent. The other thing to notice about this swarm is the timing. The M5.6 main shock was at 12:22 UTC on May 8th. The first satellite imagery showing the developing ash plume came roughly 8 hours later. That 8-hour gap is not a long time. In geological terms, it is essentially instantaneous. What that timing tells us is that the magma intrusion was massive enough and pressurized enough to crack the overlying rock cleanly and open a vent to the surface within hours. This was not a long, slow build-up followed by a gradual eruption. This was a sudden injection of fresh material that punched through the lithology above it and started erupting almost immediately. To put that in perspective, compare it to a system like Mount St. Helens. St. Helens had months of precursor activity before the catastrophic eruption in May of 1980. Earthquake swarms beginning in March, a bulge growing on the north flank, visible deformation, gas emissions ramping up over weeks. The system was telling everyone what it was about to do. St. Helens did everything that geophysics could ask of it in terms of advance warning, given the limitations of the science at the time. The central Bismarck Sea did not give us months of warning. It gave us hours. And the reason it could do that is because submarine volcanic systems, particularly fissure-fed systems, with deep magma supply, behave differently from continental stratovolcanoes. They can transition from quiescent to actively erupting on timescales that the surface volcano playbook simply does not prepare you for. And what is on the table right now, while the seismicity continues and the ash plume continues, is whether the swarm itself is going to keep escalating. If the largest event in this sequence remains the May 8th M5.6, then we are most likely watching a single large intrusion followed by a sustained but bounded eruption. If, on the other hand, we start to see new events at magnitude 5.5 or above over the coming days, that would be a signal that fresh magma is continuing to arrive at the system, that pressure is building rather than releasing, that the eruption may be in an early phase rather than at its peak. The seismic catalogue over the next 48 to 72 hours is going to be the diagnostic signal here, and as of right now, the catalogue is showing exactly what you would expect for a sustained eruption in progress. Not an escalation, not a tapering, steady. Which brings us to the part that, by every conventional measure of submarine volcanism, should not be happening at the scale we are watching. The eruption is sending an ash plume through nearly a mile of seawater and then up 9,000 feet into the atmosphere. And to understand why that single fact tells us this is not a routine submarine event, you have to understand what the pressure regime at 1,300 meters depth is actually doing to the physics of an eruption. Part 3. Through a mile of ocean. The hydrostatic pressure of seawater increases by approximately 1 atmosphere for every 10 meters of depth. At 1,300 meters, the vent of the central Bismarck Sea volcano is sitting under approximately 130 atmospheres of pressure, 1,915 pounds per square inch. That is the operational reality every gram of magma at that vent has to overcome before any of its energy can do anything visible at the surface. It is a tremendous amount of pressure. It is the kind of pressure that, in a normal submarine volcanic eruption at that depth, suppresses explosive behavior almost completely. Magma erupting at 1,300 meters typically does one of two things. It either extrudes slowly as pillow lavas, where the surface of the magma freezes into a glassy crust the instant it contacts seawater, and the molten interior continues to flow outward through cracks in that crust. Or it fragments into a relatively quiet column of steam and ash that struggles to make it to the surface, and produces at best a faint disturbance on satellite imagery. What does not happen, typically at 1,300 meters, is what is happening right now. A sustained ash plume that is breaking the surface and reaching 9,000 feet of atmospheric altitude. That is not a typical submarine eruption. That is something that requires explanation. And the explanation almost certainly involves three things operating simultaneously. The first is volatile rich magma. The chemistry of the magma being injected into the system has to be unusually gas-rich for the eruption to maintain explosive character against the overlying pressure. Andesitic and dacitic magmas in arc volcanic settings can carry several % dissolved water and carbon dioxide by weight, and when the pressure on that magma drops as it rises through the conduit, those dissolved volatiles come out of solution and expand violently. At surface eruptions, this expansion is what powers the explosive phase. At depth, the surrounding seawater pressure suppresses the expansion. For the eruption to maintain explosive character at 1,300 meters, the dissolved volatile content has to be high enough that even partial expansion against the pressure is energetic enough to drive material upward. The second is steam generation. The contact between hot magma and seawater is not gentle. The magma is at temperatures of roughly 900 to 1,200 degrees Celsius. The seawater is at near freezing temperatures at that depth, around 3 to 5 degrees Celsius. The contact produces explosive flash boiling of water into steam, and the volume expansion of that steam, against the pressure of the overlying water column, generates buoyant convective columns of mixed steam, ash, and water that can rise rapidly through the water column. These steam-driven columns are not the same as a magmatic eruption column at the surface. They are something more like an underwater geyser, scaled up by orders of magnitude, and the result is that even a moderately explosive submarine eruption can entrain enough buoyancy to break the surface and feed an atmospheric plume. The third is pumice rafts. Magma fragmenting at depth in a volatile-rich eruption produces enormous quantities of pumice, which is essentially frozen magma full of trapped gas bubbles. Pumice has a density lower than seawater. When it forms in volume, it floats. It rises through the water column and accumulates at the surface as a raft of buoyant material, which can in turn release trapped gas to the atmosphere, scatter ash into the wind, and act as a kind of secondary distribution mechanism for material that originated deep below. If the central Bismarck Sea volcano is producing pumice rafts at the surface, which is consistent with some of the early imagery we have seen, then the visible ash plume may be partly driven by atmospheric release from buoyant pumice that broke surface a kilometre or more displaced from the vent itself by ocean currents. What is happening at this volcano is most likely all three of those mechanisms operating at once. A gas-rich magma generating large volumes of steam against seawater contact, and feeding pumice rafts that are carrying additional material to the surface. The combination is what allows a vent at 1,300 meters depth to produce an ash column that reaches 9,000 feet of atmospheric altitude. And the persistence of that column over multiple days, the way it has continued to drift outward across the central Bismarck Sea visible at 40-kilometer scales on satellite imagery, tells us that the magma supply is not exhausted. The eruption is sustained. the vent is open, the system is feeding. And here is the part that is genuinely operationally significant. If a submarine vent at 1,300 meters is producing an atmospherically visible plume, it means the energetics at the vent itself are at the upper end of what submarine arc volcanism can do. It does not necessarily mean the eruption is going to escalate. Most submarine eruptions of comparable early phase character do not escalate. They proceed at roughly their current scale until the magma supply is depleted, and then they fade. But it does mean that the system has the structural and energetic conditions under which, in the rare cases where escalation does occur, you would have observed exactly this kind of pre-climax phase. The system is not a curiosity. It is a system that has demonstrated in its first days of activity that it has access to the energy budget and the volatile content required to do something much bigger than what it is currently doing. The probability of escalation is low. The conditions that would precede escalation are present. That tension is the operational reality the next several weeks will resolve in one direction or another. Now, before we go further, there is one more piece of the early imagery that needs to be addressed, because it has been circulating online and because it points at something the standard interpretation of the eruption may be missing. In the earliest Himawari satellite frames from the 8th of May, before the main ash plume becomes the dominant feature, there is an anomalous secondary surface feature visible in the data. A linear or elongated dark feature, offset from the main plume, that appears briefly and then fades as the primary column intensifies. It is faint. It is at the edge of what the imagery resolution can show. It is the kind of feature that anyone scrolling through the frames quickly would miss. And it is the kind of feature that, once you notice it, you cannot stop wondering about. Because the most natural reading of that feature is that there was something at the surface, not just at depth, in the earliest phase of the eruption. And if that reading is correct, it has implications for whether this volcano is a single vent system or a multi-vent fissure ridge. Part 4. The volcano the world forgot. Before this week, the central Bismarck Sea volcano was on no list. It was not in the public consciousness. It was not in the major volcano monitoring program watch lists. Its name is barely a name, more of a coordinate, a generic descriptor for a feature on the seafloor that the literature has never quite agreed on what to call, and the reason for that obscurity is that the central Bismarck Sea volcano has erupted exactly one time, as far as anyone has documented, in the entire span of modern volcanology. That eruption was in January of 1972. It is also how the volcano was discovered. The story of the 1972 discovery is in itself a story about how much we do not know about the seafloor. In early January of that year, hydroacoustic monitoring stations operated under the legacy of the Cold War detection networks, listening for nuclear tests under the various treaty regimes that were coming into force at the time, registered an unusual acoustic signature emanating from a region of the central Bismarck Sea. The signal was not consistent with the established fingerprints of submarine earthquakes, and it did not match the discriminants for nuclear detonations. It was longer, more sustained, lower in frequency, and it persisted in repeated bursts over a period of several days from January 8th through January 12th of 1972. Triangulation from multiple stations narrowed the source to a region of the Bismarck Sea where no volcano had been mapped. Subsequent ship-based surveys identified a fissure ridge rising from the deep abyss, with bathymetric features consistent with active or recently active volcanism, and the eruption was attributed to that system. That was it. The eruption tapered. The acoustic signal faded. The ship-based surveys filed their reports. The volcano was added to the global catalogue with a footnote and a coordinate, and no detailed bathymetric mapping beyond what could be assembled from the limited shipboard sonar of the era. And for the next 54 years, the central Bismarck Sea volcano simply sat there, in the dark, at 1,300 meters depth, with no follow-up monitoring, no permanent instrumentation, no ongoing research program. The bathymetry of the ridge has been refined modestly over the decades through opportunistic survey work by passing research vessels, but it remains, by modern standards, badly undermapped. The exact shape of the volcanic edifice, the number and location of potential eruptive vents along the ridge, the geometry of the magma supply system below. None of these are known with the kind of precision that comparable systems in the Mediterranean, the Pacific Northwest or the Hawaiian Arc would be mapped at. The central Bismarck Sea volcano is, in the most literal sense, a volcano the world has spent 5 decades forgetting about. And then, on the 8th of May, it stopped letting itself be forgotten. What we know about the system, mostly, is what its place in the broader Bismarck volcanic arc tells us. The Bismarck Arc is one of the most tectonically intricate regions of the entire Pacific Rim. The Bismarck Sea is bounded by Papua New Guinea to the south, the Admiralty Islands to the north, New Ireland to the east. Underneath that water, a complex set of microplates, the South Bismarck microplate and the North Bismarck microplate, are converging at the New Britain Trench in the south at rates that locally reach 80 to 100 millimetres per year. That is among the fastest plate convergence rates anywhere on the planet. Above that convergence, the southern Bismarck volcanic arc has produced a chain of well-known aerial volcanoes, including Ritter Island, Umboy, Sakar, Long Island, Karkar, Manam, and others. These are documented systems with monitoring programs, with eruption histories that go back centuries, with names that show up in research papers and disaster archives. The central Bismarck Sea volcano, however, is not part of that southern arc. It sits to the north, in deeper water, on what appears to be a more linear ridge structure that extends across the central Bismarck Sea, rather than tracking the curve of the New Britain Trench subduction zone. The relationship between that ridge and the broader tectonic system is itself not fully understood. One interpretation is that the ridge is associated with a secondary stress regime within the broader Bismarck microplate system, expressing magmatic activity that is not directly fed by the southern arc's subduction-generated melts, but by deeper sources within the upper mantle. Another interpretation is that the ridge is the surface expression of a rift, propagating northward from the New Britain Trench through the Bismarck Sea basin, expressing extensional rather than purely subduction-driven volcanism. The honest answer is that the research literature on this specific ridge system is thin, the bathymetric data is marginal, and the volcanic ridge under discussion has never had the kind of detailed mapping that would let us answer these questions with confidence. What we can say is that the ridge is large enough to host multiple potential eruptive vents along its length. The seismic activity we have been seeing for the past several days, spread across distances of 12 to 30 kilometres from the primary vent, is consistent with that. We can also say that the ridge geometry, rising from the deep abyss to a summit depth of approximately 1,300 metres, leaves the system fully submarine. There is no surface island here, no emergent volcanic peak, no coastline directly above the eruption. The ash plume we are seeing is breaking the surface from below, not erupting from a familiar surface vent. That fact alone changes the way the system behaves and the way it interacts with the warning architecture designed to protect coastal populations. We will come back to that. 54 years is, by submarine volcanism standards, a short dormancy. Many submarine arc systems have intervals between eruptions measured in centuries or millennia. The central Bismarck Sea volcano's transition from quiescent to actively erupting after 54 years is therefore not, by itself, unusual in the geological context. What is unusual, what is operationally striking, is the abruptness. The volcano did not give us decades of escalating unrest. It did not bulge, it did not vent gas, it did not produce a slow build-up of microseismicity that anyone was tracking. It went from silence to a magnitude 5.6 magma injection earthquake, and then from that earthquake to a sustained eruption with an atmospherically visible ash plume in a window of hours. That kind of transition is not impossible. It is consistent with deep magma supply systems where the precursor activity happens at depths below routine monitoring. But it is the kind of transition that should remind every audience watching that the dormancy of a volcano is not a guarantee of how it will behave when it returns to activity. A 54-year quiet is not a 54-year warning. It is a 54-year absence of warning until the system decides otherwise. And there is one more piece of context here that matters. The volcano has only ever been observed in eruption from the surface twice. Once by acoustic detection in 1972, once by satellite imagery this week. There has never been a direct visual observation by a research vessel of the active vent. There has never been a deep submersible deployment. There has never been a survey during eruptive activity that could characterize the vent geometry, the magma chemistry, the eruptive style with any precision. What we know about how this volcano erupts we know by inference from analog systems and from the limited observational record. That is a profound informational gap, and it is the gap that makes everything that comes next. The question of escalation, the question of flank collapse risk, the question of how the system fits into the broader Pacific picture, an exercise in working with the analogues we have rather than the data we wish we had. To the central thread, here is what this means. The system most exposed to a downstream tsunami event is also the system we know least about. The combination is what makes this story urgent. The same 54-year absence of attention that lets us forget this volcano is also the 54-year absence of mapping that means we cannot reliably forecast what it will do next. Part 5. The Ridge. The bathymetric data we do have on the central Bismarck Sea ridge is sketchy, but it tells a story when you read it carefully. The ridge is not a single peak. It is a linear feature extending across the central Bismarck Sea for tens of kilometres, with multiple high points along its length where the ridge crest approaches the 1,300 metre depth that hosts the currently active vent. Along that ridge, there are at least 3 or 4 locally elevated features that could, in principle, host independent eruptive centres. The summit topography is irregular enough that the ridge does not behave like a simple linear fissure feeding a single vent. It behaves like a volcanic chain, with the active vent as one node in a system that may have other nodes capable of activating if the magma supply propagates. That is the geometric picture that makes the spatial distribution of the earthquake swarm meaningful. When the catalogue shows events 12, 15, even 30 kilometres from the primary vent, what that distribution traces out is the broader ridge system, not just the immediate environment of the active eruption. The interpretation is straightforward. The magmatic system feeding the current eruption is connected at depth to a larger reservoir or to a propagating dike that extends along the ridge. The seismic activity in the broader region reflects that connectivity. And the operational implication is that the volcanic field is hosting one visible eruption right now, but it has the structural geometry to host more. This is the multi-vent fissure activation hypothesis. It is one of 5 interpretive frames I'll lay out for what could be happening here, and it is among the most physically plausible given the swarm distribution. The hypothesis says the central Bismarck Sea ridge is not a single vent system. It is a fissure-fed multi-node volcanic chain, and the May 8th eruption is the first eruption point along that chain to activate, not necessarily the only one. If the hypothesis is correct, what we would expect to see over the coming days or weeks is the appearance of new ash plumes from secondary vents along the ridge, separated by kilometres from the current vent, perhaps preceded by their own magnitude 4-class to 5-class earthquake swarms localised at the new vent locations. We have not seen that yet. But the geometry of the swarm has the signature of a system that could produce it. The analogues for multi-vent fissure activation come from places that have been better instrumented than the Bismarck Sea, and they tell us that this kind of behaviour is not rare. Iceland's Krafla volcanic system, during its rifting events between 1975 and 1984, repeatedly produced eruptions at different points along a fissure swarm that extends for tens of kilometres, with each individual eruption episode lasting weeks to months, and the broader system activating different vents along the fissure over the course of years. The East African Rift system, in its various Holocene eruptive episodes, has shown comparable behaviour. The Reykjanes Peninsula in Iceland, with the recent sequence of eruptions beginning in 2021, has demonstrated the same pattern at a more compressed timescale, with successive eruptions appearing at locations separated by kilometres along an active fissure system. The central Bismarck Sea ridge, if the hypothesis is correct, is operating in this kind of regime, even if we have not yet observed the second vent. And here is why this matters for the central tsunami risk thread. A multi-vent activation does not, by itself, increase the immediate risk of a flank collapse. Each individual vent is producing its own contribution to the load on the volcanic edifice, and a single active vent is no more or less likely to destabilise the slope than the first eruption of a single vent system would be. But a multi-vent activation extends the duration over which the system is in an elevated risk state. Instead of a single eruption that runs for some number of weeks and then ends, returning the system to baseline, a multi-vent activation can extend the active phase to months or longer, with the elevated probability of flank collapse triggering events accumulating over the longer duration. If the central Bismarck Sea ridge is in the first eruption of a multi-vent sequence, then the period of elevated tsunami risk is not a few weeks. It is potentially much longer. The geometry also matters for where a flank collapse would originate if one were to occur. A single vent system with a localized cone has a flank collapse geometry that is reasonably predictable, with the collapse most likely to occur on the side of the cone that is most steeply graded or that has accumulated the most material. A multi-vent ridge system, by contrast, has multiple potential collapse origin points, each with its own slope geometry, and the resulting debris path could propagate in any direction along the ridge. Predicting where a collapse would impact, if one occurred, becomes a higher dimensional problem on a poorly mapped ridge than it would be on a well-mapped cone. There is one more piece of the ridge geometry that the literature suggests, but cannot confirm with the current bathymetric data, and it is worth flagging because it would be a significant escalation factor if it turns out to be true. Some interpretations of the limited bathymetry have suggested that the central Bismarck Sea ridge may have already produced one or more major flank collapse debris fans in its prehistoric record, with the resulting bathymetric signatures showing up as scour features on the deep abyssal plain to one side of the ridge. The Silver et al. 2008 study of the Bismarck volcanic arc, which we'll cover in Part 8, focused primarily on the southern arc and did not extend its detailed bathymetric coverage to the central Bismarck Sea ridge with the same resolution. The possibility that the central ridge is itself a flank collapse-prone system with prehistoric collapse events in its record cannot be confirmed or ruled out from current data. If it is, then the 1888 Ritter analogue is even more directly applicable than we have been treating it. We do not know. The data to know is one detailed bathymetric survey away, and that survey has never been done. Part 6. The anomaly in the imagery. There is something in the earliest Himawari satellite frames from May 8th that I want to walk through carefully because I have not been able to find a fully convincing explanation for it, and I think the audience should see it the way the data actually shows it. In the frames captured immediately before sunrise UTC, when the angle of solar illumination is just barely sufficient to reveal surface features, there is a faint linear feature visible at the surface of the central Bismarck Sea, offset from the location where the main ash plume will subsequently emerge. The feature is elongated. It extends in roughly a westward direction from a point slightly displaced from the primary plume source. It is darker than the surrounding water at that illumination angle, which is consistent with either a surface boil-off of seawater into low-altitude steam, with a floating raft of fragmented volcanic material, or with a transient secondary plume from a separate vent that has since faded. As the imagery loop continues through sunrise and the primary ash plume develops into the dominant visible feature, the secondary feature fades. By the time the morning passes and the imagery is showing the well-developed plume that Volcano Discovery and the Darwin VAC are reporting on, the secondary feature is no longer distinguishable from the broader area of disturbed water surrounding the eruption site. It exists on the imagery for a window of perhaps 45 minutes to an hour at the very onset of the visible eruption phase, and then it is gone. There are several interpretations of this feature that need to be on the table, because each of them has different implications for what the eruption actually looks like at the surface and what the underlying ridge geometry is doing. The first interpretation, which a chat moderator suggested in real time during the original observation, is that the feature is a current advected initial steam plume. Under this reading, the early phase of the eruption produced a localized boil-off of seawater into steam at the surface, which was then advected by surface currents away from the actual eruption point by a kilometre or more before the main plume mechanism stabilized. The angle of solar illumination at sunrise rendered the displaced steam plume visible briefly, before the main plume scale overwhelmed the early signal. This interpretation is plausible and consistent with what we know about how steam-driven submarine eruptions evolve. It explains why the feature is offset from the main plume location. It explains why it fades as the main eruption stabilizes. It does not require any additional eruption physics beyond what is already in the conventional model. The second interpretation is that the feature is a pumice raft. As we discussed in Part 3, eruptions at depth that produce volatile rich magma can fragment into pumice, which floats and accumulates at the surface in rafts. If the initial pulse of the eruption produced a large enough volume of pumice to form a visible raft, that raft would have been advected by surface currents away from the eruption point, just like a steam plume would be. The pumice raft interpretation is also consistent with the offset location. It is consistent with the eventual fading of the feature as the raft disperses under wind and wave action, and it is consistent with a key piece of operational reality, which is that submarine eruptions that produce visible ash plumes at the surface typically also produce significant pumice raft populations that can persist as drifting hazards to shipping for days to weeks after the event. The third interpretation, and the one that has implications for the multi-vent hypothesis, is that the feature is a secondary vent that was briefly active during the first phase of the eruption and then either ceased activity or was overwhelmed by the dominant primary vent. Under this reading, the central Bismarck Sea ridge was opening simultaneously at multiple points during the magma intrusion event, with the secondary vent producing a brief surface signature before its supply was redirected or its conduit closed. This interpretation is harder to verify from the available data, but it would be the most operationally significant of the three, because it would constitute direct early evidence that the ridge is hosting multi-vent activation, and would therefore extend the elevated risk timeline as discussed in Part 5. Among the three, I think the most likely is the second one, the pumice raft interpretation, with the first one, the current advected steam plume, as the runner-up. The third interpretation is possible but harder to support without additional observations. What I want to be clear about, though, is that none of the three interpretations is fully testable from the imagery alone. A research vessel deployed to the central Bismarck Sea over the next several days, capable of sampling the water and the surface debris in the vicinity of the eruption, could resolve which interpretation is correct. Such a deployment has not been announced as of this recording. The interpretation will probably remain ambiguous until the imagery is reanalyzed in light of later observations. What matters for the central tsunami risk thread is this. The anomaly in the imagery is a reminder that we are watching a system in motion with marginal real-time information. The features that show up in the first frames of a major event are often the features that turn out, in retrospect, to have been the most diagnostic. If the secondary surface feature was a secondary vent, then the system is more complex and the elevated risk window is longer than the simplest interpretation would suggest. If it was a pumice raft, then the eruption is volatile rich, and the kind of pre-climax signature that the rare paroxysmal events have historically shown is present. If it was a current advected steam plume, then the system is behaving in a relatively conventional submarine eruption manner. All three interpretations have implications for what to watch for next, and all three keep the tsunami risk question very much alive. Part 7. The Ghost of Ritter. To understand why everyone who has been paying attention to the central Bismarck Sea is talking about tsunami risk, you have to go back to March of 1888, and you have to look at what happened approximately 200 kilometers south of the current eruption, on an island called Ritter, in the southern Bismarck volcanic arc. Ritter Island, before March of 1888, was a stratovolcanic island in the southern Bismarck arc. It was an aerial volcano. You could see it. It rose out of the sea. It had a clear edifice, a defined summit, slopes that descended into the surrounding waters. It was not a notable feature on the global volcanic map, because it had not produced any major historical eruption that we have on record, but it was there, and the indigenous populations of the surrounding islands knew it, and ships transiting the Bismarck Sea knew to give it some distance because of occasional mine activity in the late 19th century. Then, in the pre-dawn hours of March 13th, 1888, Ritter Island ceased to exist as a structure. The mechanism is what makes this event the operational anchor for everything we're watching right now. The volcanic edifice of Ritter Island became unstable. The exact trigger has been debated in the literature, with some interpretations favouring an ongoing eruption that overpressurised the western flank, and others favouring a smaller seismic event that destabilised a slope that was already on the edge of failure. Whatever the trigger, the result was a catastrophic sector collapse. The western flank of the volcano, somewhere between 1 3/4 and several cubic kilometres of rock and ash and crystallised lava, detached from the structure as a coherent debris mass and slid into the sea. The volume that broke loose has been estimated at approximately 4.6 cubic kilometres based on the bathymetric mapping of the resulting debris fan, which is one of the largest documented submarine landslides in the historical record. The mass slid down the volcanic flank into the surrounding ocean and across the seafloor at speeds estimated at 40 metres per second or greater. 40 metres per second is approximately 144 kilometres per hour, 90 miles per hour. That is fast for any Earth surface process. It is extraordinarily fast for a mass with the volume of 4 cubic kilometers. The kinetic energy involved is staggering. What followed was a tsunami. The mass entering the water displaced a volume of ocean approximately equal to its own volume, transferring its kinetic energy into the surrounding water column and generating waves that radiated outward from the collapse site. The mechanism is what distinguishes landslide-generated tsunamis from the more familiar earthquake-generated tsunamis. Earthquake tsunamis are produced by the vertical displacement of the seafloor along a rupture, which displaces a column of water above it and generates waves whose amplitude depends on the rupture geometry and the depth of the displacement. Landslide tsunamis are produced by the impulsive momentum transfer from a moving mass into the surrounding water, and their amplitude depends on the volume of the slide, the velocity of the slide, the depth of the water at the source, and the proximity of coastlines to the source. Landslide tsunamis can be locally much larger than earthquake tsunamis from comparable energy budgets, because the momentum transfer is more concentrated and the displacement is more violent. The run-ups documented from the Ritter event are staggering even today, more than a century later. The closest islands, Umboy, Sakar, and the western shores of New Britain, all within approximately 50 kilometers of the Ritter collapse, registered the destruction. Trees were stripped from the lower slopes of these islands at heights of approximately 15 meters above sea level, which is the diagnostic feature that the survey teams use to estimate the run-up. Because trees can survive partial overtopping by a tsunami up to a fraction of their height before they are uprooted, the actual peak run-up is interpreted to have been in excess of 15 meters at these locations. The literature estimates the actual peak run-ups were in the range of 20 to 50 meters at certain locations on the adjacent islands. 50 meters is more than 160 feet. That is taller than a 15-story building. That is the height of water that overran the coastlines closest to Ritter on the morning of March 13th, 1888. The death toll on those coastlines has been documented at several hundred. The number is not precise. The record-keeping in the Bismarck Sea region in the late 19th century was incomplete, and the indigenous populations affected by the event did not produce continuous written records. But the documented dead, across the immediate coastlines, is in the several hundred range, and the actual toll is probably higher when undocumented losses are included, and the damage propagation extended much further than the immediate vicinity. The literature documents significant tsunami effects, including coastal flooding, structural damage, and disrupted shipping, at distances of up to approximately 600 kilometers from the Ritter source, that is the entire western Bismarck Sea basin, and into the adjacent waters. A landslide-generated tsunami from a single flank collapse on a single volcanic island produced impacts across an area on the scale of an inland sea. That is the event. That is what happened in 1888. And the reason this matters for what we are watching tonight is that the central Bismarck Sea volcano sits in the same arc system as Ritter, approximately 200 kilometers north of where Ritter used to be. The structural conditions that allowed Ritter to fail, an unstable volcanic edifice with steep slopes, an active eruption stressing the structure, surrounding water deep enough to allow the slide to develop kinetic energy, but shallow enough to translate that energy into surface wave amplitude, those conditions are not unique to Ritter. They are conditions that the Bismarck arc as a whole has demonstrated it can produce, and the central Bismarck Sea volcano, while structurally distinct from Ritter in important ways, is producing the same kind of operational signature: sustained eruption, ongoing seismic swarm, deep submarine setting on a poorly mapped ridge that you would want to watch carefully for the warning signs of a comparable event. The differences between Ritter and the central Bismarck Sea volcano matter too, and they matter in both directions. Ritter was an aerial volcano. Its mass was sitting above the waterline, exposed to atmospheric weathering and to the destabilizing effects of full atmospheric pressure differentials. The central Bismarck Sea volcano is fully submarine. Its edifice is under 1,300 meters of water. The hydrostatic damping effect of that overlying water column reduces, but does not eliminate the amplitude of any tsunami that a comparable volume collapse would generate. The depth dependence of submarine landslide-generated tsunamis is well documented in the technical literature on landslide tsunamis, and the rule of thumb from the Hampton-Lee-Locott framework is that for a fixed slide volume, doubling the water depth at the source roughly halves the peak run-up at adjacent coastlines. A comparable volume collapse at the central Bismarck Sea ridge, at 1,300 metres depth would therefore produce run-ups on the order of 1/5 to 1/2 the Ritter run-ups, translating to peak run-ups in the 8 to 25 metre range at the nearest islands. That is still catastrophic. 8 to 25 metres of water arriving at a coastline is the kind of event that kills people and destroys infrastructure across kilometres of shoreline. It is just not the 50-metre Ritter scale. The other difference is that the central Bismarck Sea ridge is structurally more distributed than the Ritter cone was. A multi-vent ridge does not have a single collapse mass with a clearly defined failure geometry. It has multiple potential failure points along a ridge, each with its own slope geometry, and the resulting collapse volume in any single event might be smaller than the Ritter mass. Smaller debris volumes produce smaller tsunamis. The expected adverse impact at adjacent coastlines, if a collapse were to occur on the central ridge, is probably less catastrophic on a per-event basis than what Ritter delivered. The total elevated risk envelope is potentially longer in duration because of the multi-vent geometry, but the per-event amplitude is probably lower. But the qualitative point is what matters. The Bismarck Arc has produced one mass casualty flank collapse tsunami in the historical record, and the conditions that produce that event are present in modified form at the central Bismarck Sea volcano right now. The Ritter event is not an abstraction. It is a documented event with a death toll and a damage envelope, and it is the right historical anchor for thinking about what the worst case for the current eruption could look like. And if anything, the worst case is worse than just Ritter, because Ritter is not the only mass casualty tsunami this region has produced. There is a second event in July of 1998 that nobody calls by name anymore because it has been overshadowed by the Indian Ocean tsunami of 2004 and other later catastrophes, but that killed more than 1,600 people in a single afternoon, the Itape tsunami. And the Itape event tells us something important about how flank collapse style mechanisms can produce catastrophic surface waves without the kind of advanced seismic warning the conventional tsunami warning system is designed to detect. Because the trigger at Itape was not a great megathrust earthquake. It was a moderate magnitude 7 event that destabilized a submarine landslide on the continental slope, and the warning system in the time available did nothing. Part 8. The Catalogue of Failure. The Silver et al. 2008 paper in the Journal of Volcanology and Geothermal Research, titled Volcanic Collapse and Tsunami Generation in the Bismarck Volcanic Arc, Papua New Guinea, is the single most important piece of published research on what we are watching tonight. It is not new. It is more than 15 years old, but it remains the most comprehensive bathymetric and forensic survey of the Bismarck Arc's flank collapse history. And what it found, when you read it carefully, is that the Ritter event was not an outlier. The Ritter event was the most recent in a long sequence of flank collapse events that have been a regular feature of this volcanic arc throughout its geological history. The Silver paper used a combination of side-scan sonar surveys, high-resolution multi-beam bathymetry, and analysis of pre-existing surveys to map the seafloor of the Bismarck Arc in detail across the southern and central segments of the arc. The team identified, mapped, and classified 12 distinct debris fans across the arc, each interpreted as the surface signature of a major flank collapse event from a volcanic edifice in the arc system. The footprints of these debris fans range from approximately 20 square kilometres for the smallest events up to approximately 150 square kilometres for the largest. 12 documented flank collapse events across a single volcanic arc is a remarkable concentration of mass failure activity, and what it tells us is that flank collapse in this arc is not a rare event on geological timescales. It is a recurring feature of how the arc evolves. The Ritter debris fan, which the team mapped in greater detail than most of the other fans because of the historical record associated with it, is among the larger fans on the arc, with the 4.6 cubic kilometre volume corresponding to a footprint of several tens of square kilometres and a debris extent that reaches up to 35 kilometres from the source island. The largest blocks of debris in the Ritter fan are concentrated within 15 kilometres of the source, with smaller and more densely packed blocks beyond that as the debris dispersed during the slide. The team used the size distribution and the angular geometry of the blocks to constrain the velocity of the slide at 40 metres per second or greater, which is the figure we discussed in Part 7, and to infer the time evolution of the slide as it propagated across the seafloor. But the 12 fans the Silver team identified are not all Ritter-class events. Several of them are larger, Several of them are smaller. They span a range of estimated volumes from less than 1 cubic kilometre to potentially much larger than the Ritter 4.6. They span a range of estimated ages from approximately the past 100 years, in the case of Ritter, and possibly one or two other Holocene events, back to perhaps 50,000 years in the case of the oldest fans for which the radiometric and stratigraphic dating could be constrained. 12 mass failure events distributed across approximately 50,000 years of arc history implies an average return interval across the entire arc of approximately 4,000 years per location for events large enough to leave detectable bathymetric signatures. That number, 4,000 years per location, sounds long, and on a human timescale it is very long, but on a volcanic system timescale it is short. A volcanic arc that is producing a documented mass failure event every 4,000 years is an arc whose flank collapse hazard is a normal, recurring feature of its evolution rather than a rare anomaly. And what that implies for the central Bismarck Sea volcano is that the question of whether the present ridge has produced flank collapses in its own geological past is not if, but when, with the most likely answer being yes, repeatedly, just below the resolution of the current bathymetric coverage of the ridge. The Silver team also examined the relationship between flank collapse and the broader tectonic and volcanic state of the arc. The team found that the larger collapses tend to be associated with periods of elevated arc-wide volcanic activity in which multiple volcanic centres are simultaneously in active eruption or recent eruption. This is not deterministic, it is a statistical association. But what it suggests is that the structural conditions that promote flank collapse, an active edifice with internal pressure variations, with ongoing seismicity, with the kind of magma intrusion that destabilises the slope geometry, are conditions that occur preferentially during arc-wide activity peaks. Whether the May 2026 Western Pacific Volcanic Cluster qualifies as an arc-wide activity peak in the sense the Silver team meant is debatable, but the cluster is not zero, and it is not nothing, and the cluster is happening at the same time the central Bismarck Sea volcano is doing what it is doing. The correlation is not necessarily causal, and chance clustering of arc activity is a real possibility, but the alignment is operationally relevant. There is one more piece of the Silver paper that I want to highlight, because it has implications for how we should think about warning architecture. The paper documents that several of the Bismarck Arc flank collapse events appear to have occurred without any preceding seismic signal large enough to have triggered a regional warning. The flank collapse mechanism, particularly for events on the order of 1 to 4 cubic kilometres, is a gravitational failure that does not require a discrete earthquake trigger. The structure becomes unstable through cumulative loading and pressure changes during volcanic activity, and at some point the failure threshold is exceeded and the collapse occurs. The resulting tsunami can propagate with no advance warning at all until coastal sensors registered the wave itself, by which time arrival times on the nearest coastlines are inside the windows the entire warning architecture is meant to provide. This is the structural reason why volcanic flank collapse is taken so seriously, even when the seismic record is quiet. The mechanism evades the standard warning system by design, and that brings us to Itape. Part 9. Itape and why the warning system is not designed for this. On the afternoon of July 17, 1998, on the northern coast of Papua New Guinea, west of the Sepik River mouth, near a town called Itape, the ocean retreated from the shore. The water pulled back several hundred metres, exposing the seafloor that local people had never seen except at the lowest tides. Children ran out onto the exposed sand to look at the fish flopping in the tide pools. Within minutes, the water came back. It came back as 3 successive waves, the largest of them estimated at more than 10 metres tall, breaking across the coastal villages of Sisano, Warapu, Arop and Malol. Within those few minutes, 1,600 people died. Some sources put the number higher, some put it slightly lower. The exact toll is debated. What is not debated is that the Itape event of July 17, 1998 was one of the deadliest tsunamis in modern Papua New Guinea history, and that the warning system that exists today did not warn anyone. The trigger for the Itape tsunami was an earthquake, a magnitude 7.0 event which struck the offshore region a few kilometres north of Itape at approximately 1849 local time. A magnitude 7 is significant. It is the kind of event that, in the conventional understanding of tsunami generation, can produce a destructive tsunami if it occurs on a shallow thrust fault near a coastline. But the magnitude 7 at Itaipei was not a thrust event of the kind that conventionally produces a large tsunami. It was a strike-slip event, and the immediate vertical displacement of the seafloor that the earthquake itself produced was not, by the standard models, sufficient to generate the wave heights that subsequently struck the coast. The conventional model, applied to the magnitude 7, would have predicted a tsunami of perhaps 1 to 2 meters at the coast. What arrived was more than 10 meters. The reason for the discrepancy is what makes Itaipei directly relevant to what we are watching tonight. The actual tsunami at Itaipei was not generated by the earthquake itself. It was generated by a submarine landslide that the earthquake triggered. The continental slope offshore of Itaipei has steep, sediment-laden bathymetry, with accumulated unstable material that had been building up over thousands of years. The magnitude 7 earthquake was sufficient to push the slope past its failure threshold, and a large mass of sediment and rock slid down the continental slope into deeper water. The momentum transfer from that slide into the surrounding ocean generated the destructive waves that subsequently struck the coast. The earthquake was the trigger. The landslide was the mechanism. Why this matters for the central Bismarck Sea volcano is that it demonstrates, with 1,600 bodies of evidence, that a moderate seismic event can produce a catastrophic tsunami when the underlying slope geometry is unstable and the failure mechanism is gravitational rather than directly seismic. The conventional tsunami warning system, which relies on detecting large earthquake signatures to issue regional warnings, did not warn for Itaipei because the earthquake itself was not the kind of event the system is designed to flag. The warning architecture issued only a localized advisory after the wave was already breaking across the coast. By the time the system had any information about what was happening, the dying was already over. The structural lesson of Itaipei, formalized in the years since by the international tsunami warning community, is that there is a class of tsunami events that the conventional warning system cannot reliably detect in advance. These events are produced by submarine landslides, volcanic flank collapses, and other gravitational failures whose surface manifestation is a wave, but whose seismic signature is either absent or insufficient to trigger an automated response. The Pacific Tsunami Warning Center has, in the years since Itaipei, invested heavily in coastal sensor networks, in deep ocean assessment buoys, and in tsunami source modelling that can detect the wave once it has propagated through deep water far enough to reach the buoys, but the time gap between the source of a landslide tsunami and its arrival at the nearest coastline is often shorter than the propagation time to the nearest assessment buoy. The warning system catches up to the wave only after the wave has done its damage. For the central Bismarck Sea volcano, the operational implication is direct. If a flank collapse were to occur on the central ridge, with a debris volume even 1/4 of the Ritter volume, the resulting tsunami could propagate to the nearest inhabited coastlines of Manus Island to the north, or the islands of the southern Bismarck Arc within minutes. Whatever warning the Pacific Tsunami Warning Center is able to issue in that scenario would arrive at the affected coastlines after the wave. The protection that exists for those coastlines is not advance warning. It is the structural integrity of the volcano edifice itself, and that integrity is being stressed right now by the sustained eruption and the ongoing earthquake swarm. This does not mean the warning system is broken. It does mean the warning system is the wrong frame for thinking about this kind of risk. The frame that matters is the one in which the threat lives in the geometry of the volcanic edifice itself, and the warning is the eruption you are watching tonight. The eruption is not the threat directly. The eruption is the warning that the system is in an elevated risk state. The threat is the downstream event the eruption may or may not produce, and the protection is whatever decisions can be made about coastal preparedness in the days and weeks between the eruption beginning and any potential downstream event occurring, with the understanding that the conventional warning architecture will not provide a separate warning at the moment of collapse, if collapse occurs. That is the truth of the situation. It is uncomfortable. It is the part of the story that does not fit into a clean narrative of, the warning system will keep us safe. For the central Bismarck Sea, the closest analogue to a warning system right now is the satellite imagery showing the ash plume, the catalogue of earthquakes showing the swarm, and the historical record telling us what the worst case looks like. That is the warning. The audience watching this tonight is part of the warning system, in the sense that public awareness of the elevated risk is the only mechanism by which coastal populations in the affected region can make any decisions about what to do over the next several weeks. The eruption is the warning. The Ritter Island debris fan, 200 kilometers south of the current eruption, mapped in detail by the Silver team and resting at the bottom of the Bismarck Sea, is the warning. The 1,600 dead at Itape, who had no warning at all, are the warning. What we have not yet talked about is what the absolute upper limit of how this could escalate looks like. Because while Ritter is the historical anchor for what flank collapse can do at scale, and Itape is the structural anchor for why warning systems fail, there is one more anchor that has to be on the table, and that is the largest documented volcanic eruption of the 21st century, 4 years ago, in another underwater volcanic system in the Western Pacific. Hunga Tonga. Part 10. The Ceiling. On the 15th of January, 2022, in the South Pacific Ocean, several hundred kilometers north of the main island of Tongatapu in the Kingdom of Tonga, an underwater volcano called Hunga Tonga Hunga Ha'apai produced what has now been confirmed as the largest volcanic eruption of the 21st century. The eruption was rated at approximately Volcanic Explosivity Index 5.8. The eruption column reached an altitude of approximately 55 to 58 kilometers, breaking through the troposphere, breaking through the stratosphere, reaching into the mesosphere. Water vapor was injected into the stratosphere at a mass estimated at approximately 150 megatons. That is 150 million metric tons of water, lifted from the ocean into the upper atmosphere by the energetics of a single volcanic event. The atmospheric pressure wave from the eruption circled the entire planet, was detected on barometers in every country, and was visible on weather satellites as it propagated around the globe more than once. Tsunamis from the eruption were detected on coastlines as far as Peru, where 2 people died from related coastal effects, and as far as California, where the wave was detected and produced flood warnings up the entire west coast of the United States. That is what an underwater volcanic eruption can do, at the upper limit of what the modern record contains. It is the operational ceiling for what the central Bismarck Sea could become, in the very worst-case scenario that is on the table, and it is important to look at the ceiling honestly, because the Hunga Tonga eruption was, in many ways, the kind of event that the rest of the scientific community had been treating as a hypothetical worst case for submarine arc volcanism for decades. The hypothetical worst case turned out to be a real event. It happened. The literature on what submarine volcanic systems are capable of, at their absolute most extreme, has been rewritten since January of 2022. The pre-climax phase of the Hunga Tonga eruption is what I want to focus on, because it is the phase that is most directly comparable to what the central Bismarck Sea is doing right now. On the 14th of January 2022, the day before the paroxysmal event, Hunga Tonga was producing a sustained explosive eruption that was visible on satellite imagery as an active vent producing ash plumes that was generating an active seismic signal recorded on regional networks, and that was demonstrating exactly the kind of underwater to atmospheric ash transport that the central Bismarck Sea volcano is demonstrating tonight. On January 14th, 2022, the Hunga Tonga eruption was being reported as a significant but bounded event. By the morning of January 15th, it had become the largest volcanic eruption of the century. The transition happened in a window of hours. This is the part that requires extreme care in how it gets framed. The pre-climax phase of Hunga Tonga is operationally similar to what we're watching at the central Bismarck Sea right now. The post-climax events at Hunga Tonga are operationally catastrophic. The straightforward question is whether the operational similarity in the pre-climax phase is predictive of operational similarity in what comes next, and the honest answer is that it is not. The history of submarine volcanism over the past 50 years contains many events that produced pre-climax phases broadly similar to what Hunga Tonga showed on January 14th of 2022, and that did not subsequently produce paroxysmal events. The Kasatochi eruption of 2008 in the Aleutian Arc, the Sarychev eruption of 2009 in the Kuriil Arc, various submarine eruptions in the Mariana Arc that have been documented by ocean exploration vessels in the Ring of Fire program. Several of the Bismarck Sea's own historical events. These are systems that produce sustained ash plumes from submarine vents that exhibited active seismic swarms, that drew the attention of regional volcanological agencies, and that subsequently tapered off at relatively modest scales without escalating to anything approaching Hunga Tonga. The base rate for paroxysmal escalation from a pre-climax phase like the one we are watching is low. Most events that look like this do not become this, but low does not mean zero, and the rare events that do escalate are catastrophic, at scales the modern record had not previously contained. The Hunga Tonga eruption killed at least 4 people directly through its tsunamis, with the total economic impact across the Kingdom of Tonga and the broader Pacific in excess of $200 million in 2022 currency. The water vapour injection has contributed to measurable changes in stratospheric chemistry and middle atmosphere radiative balance that are still being studied 4 years later, with research indicating contributions to Antarctic ozone variability, to short-term global mean temperature variability, and to atmospheric dynamics on timescales of multiple years. The pressure wave alone disrupted satellite communications, atmospheric measurements, and aviation operations across multiple continents in the hours after the eruption. The honest framing for the central Bismarck Sea, therefore, is that the worst-case ceiling is genuinely Hunga Tonga class, and the probability of reaching that ceiling is low single-digit % over the duration of the present eruption. That is not a prediction, it is a probability estimate. The probability is low, the probability is not zero, and the difference between low and zero is what makes this an event that everyone who can pay attention to the Western Pacific should be paying attention to, even though the most likely outcome is that the central Bismarck Sea volcano produces a sustained but bounded eruption that runs for a few weeks and then tapers off. The reason Hunga Tonga is on the table at all is that the central Bismarck Sea event has demonstrated in its first 5 days that it has access to the energy budget and the volatile content required to maintain an atmospherically visible plume against the hydrostatic pressure of more than a mile of seawater. That is the diagnostic feature of the Hunga Tonga pre-climax phase. It is the feature that distinguished Hunga Tonga from the dozens of other submarine eruptions that did not subsequently escalate. The Bismarck Sea event has that feature. Whether it will also have the additional features, the specific magma-water interaction physics, the specific pressure trajectory in the magma chamber, the specific geometry of the surface eruption that allowed Hunga Tonga to undergo its terminal explosive transition is unknown. The conditions that distinguish ordinary submarine eruptions from Hunga Tonga class events are an active area of research, and the discriminating features are not fully understood. The Bismarck Sea volcano might have them. It probably does not. Probably. For the central tsunami thread, the Hunga Tonga ceiling has a specific implication. A Hunga Tonga scale paroxysm at the central Bismarck Sea would produce a Hunga Tonga scale tsunami. The Hunga Tonga tsunami was detected globally, with peak run-ups on the order of 15 metres at the immediately adjacent coastlines of Tonga, and with destructive coastal effects across the South Pacific. A comparable event at the central Bismarck Sea, with adjacent inhabited coastlines on Manus Island and the southern Bismarck Arc, would produce immediate catastrophic impacts at those coastlines, and would propagate destructive waves across the entire Western Pacific basin. That is the upper bound on what we are watching. The probability remains low, the bound is real. Part 11. The Cluster. While the central Bismarck Sea volcano has been doing what it is doing, a remarkable cluster of significant volcanic activity has been unfolding across the rest of the Western Pacific in the first 2 weeks of May 2026. 6 distinct volcanoes in 6 different volcanic arcs, all in some kind of elevated state simultaneously. This is the part of the story that we have to look at carefully, because what is going on across the Western Pacific at this exact moment is either a remarkable coincidence, or it is evidence of something larger happening at the scale of the entire Pacific plate, and the difference between those two interpretations matters for how to think about the central Bismarck Sea event in its broader context. The first system in the cluster is Sakurajima, in southern Kyushu, Japan. Sakurajima is part of the Aira caldera complex sitting in Kagoshima Bay just across the water from the city of Kagoshima itself, where 600,000 people live within 4 kilometers of an active volcano. Sakurajima has been continuously active in various modes since 2017, with frequent Volcanian explosions producing relatively small ash columns and occasional larger events producing more substantial plumes. On the 8th of May 2026, Sakurajima produced what the Japan Meteorological Agency described as a significant explosive event from Minamidek crater, with a plume reaching 3,500 meters above the summit and ballistic ejection extending to over a kilometer from the crater. The crucial qualitative feature of this event, the feature that distinguishes it from Sakurajima's routine activity, is that it produced a pyroclastic flow. the first pyroclastic flow at Sakurajima in approximately 8 years, according to JMA. A pyroclastic flow is qualitatively different from a Volcanian explosion. It is the kind of event that indicates significant structural change in the eruptive system, and it is the kind of event that warrants close attention from monitoring agencies because of its potential to escalate further. The second system is Mayon Volcano in Albay province on Luzon, Philippines. Mayon is the Philippines' most active volcano, with a long history of paroxysmal eruptions producing pyroclastic density currents that have killed hundreds of people in the past 2 centuries. In early May 2026, Mayon entered a phase of elevated activity, with PHIVOLCS, the Philippine Volcano Monitoring Agency, raising the alert level to 3 on a 5-point scale. Pyroclastic density currents began on the 5th of May and have continued, with ash plumes, rockfalls and crater incandescence documented through the recording of this video. Mayon is a stratovolcano with a particularly steep summit cone, which makes it especially prone to flank failure-driven pyroclastic flows when its eruptive activity intensifies. The ongoing PDC activity since May 5th is the most significant pulse of Mayon eruptive behaviour in approximately 3 years. The third system is Mount Dukono on Halmahera Island in North Maluku, Indonesia. Dukono is a relatively obscure stratovolcano that produces persistent low-level explosive activity. In early May, Dukono produced an ash plume that, according to reports, reached approximately 11,000 metres above sea level. 11,000 metres is significant because it is the approximate altitude of the local tropopause, the boundary between the troposphere and the stratosphere. Volcanic ash injected to altitudes above the tropopause has substantially longer atmospheric residence times and broader dispersion patterns than ash that remains in the troposphere. Reaching the tropopause is not Hunga Tonga territory by any stretch, but it is well outside the routine eruptive envelope for most volcanoes globally, and the fact that Dukono is producing tropopause-reaching ash is the diagnostic feature that puts it on the cluster watch list. The fourth system is Canlaon in Negros Occidental, Philippines. Canlaon has been in a state of low-level unrest through early 2026, with elevated seismicity and gas emissions documented by PHIVOLCS. The state of unrest has been escalating gradually, rather than producing a discrete paroxysmal event, with the alert level rising and the monitoring intensity increasing as the system has shown signs of fresh magma intrusion at depth. Canlaon has not yet produced a major eruption in 2026, but it is on a trajectory that suggests significant escalation is plausible over the coming weeks to months. The fifth system is Lewatobi Laki-Laki on East Flores in the Lesser Sundas region of Indonesia. Lewatobi Laki-Laki is one of 2 adjacent volcanoes, the female and the male, that make up the Lewatobi complex. Between the 1st and the 11th of May 2026, the Indonesian Volcanic Monitoring Agency PVMBG, operating through its Magma Indonesia portal, observed and reported a substantial increase in indicators of unrest at Lewatobi Laki-Laki, including increasing gas emissions detectable by satellite, measurable ground deformation, increasing ground tremor, deep volcanic earthquakes consistent with magmatic intrusion, and rising magmatic pressure based on tilt and inflation data. On the basis of these observations, PVMBG raised the alert level from 2 to 3 on a 4-point scale. An alert level increase from 2 to 3 is the kind of escalation that monitoring agencies do not declare lightly. It implies the system has crossed a defined threshold of unrest, and is moving toward eruption rather than away from it. The sixth system is the Central Bismarck Sea volcano, which is the focus of this entire video. That is 6 systems, across 6 different volcanic arcs, in the first 2 weeks of May 2026, all exhibiting some form of elevated activity or significant eruption. This is not a routine state for the Western Pacific. The Smithsonian Global Volcanism Program documents that on average, the Western Pacific Basin has perhaps 2 to 4 volcanoes in some form of elevated state at any given time. 6 concurrent systems is on the high end of that range, and the qualitative character of the activity, with 1 paroxysm, 2 systems producing pyroclastic flows or density currents, 1 tropopause reaching plume, 2 alert level escalations, and 1 submarine eruption that is the most significant submarine event since Hunga Tonga, is unusually intense. Whether this cluster constitutes evidence of something larger than chance is an open question. The most defensible answer is that it could be chance. Volcanic activity is heterogeneous in time, with bursts of activity separated by quieter intervals, and a 2-week window with 6 significant events is within the statistical envelope of normal Western Pacific volcanic behaviour. The geological record is full of comparable clusters that turned out, on close examination, to have no shared cause. The pattern recognition that humans naturally apply to events like this can be misleading. 6 volcanoes erupting in 2 weeks across the entire Western Pacific is, in the long-run frequency sense, not as unusual as it feels to the people watching it happen. But there is a less conservative reading, and that reading is the one we have to address. The Pacific Plate is the largest tectonic plate on Earth, covering nearly half the planet's lithospheric surface. The boundaries of the Pacific Plate produce most of the world's significant earthquakes, most of the world's significant volcanic activity, and most of the world's significant tsunami sources. The Pacific Plate is in continuous motion, with convergence rates at its arcuate margins running from 60 to 100 mm per year along most segments. Sustained flexure of the Pacific Plate, large-scale convection-driven mass redistribution within or beneath the plate, episodic stress redistributions across the entire boundary could in principle modulate volcanic and seismic activity simultaneously across multiple subduction arc systems. This is not crazy. It is the kind of hypothesis that has received increasing attention in the geophysics literature over the past decade, as detection capabilities for plate-scale phenomena have improved. Part 12. The Coupling Hypothesis. The Pacific Plate Dynamical Coupling Hypothesis says, the May 2026 Western Pacific Volcanic Cluster reflects coupled dynamical changes at the scale of the entire Pacific Plate, with the broader stress state of the plate modulating volcanic activity at multiple arc systems simultaneously. The hypothesis is consistent with a broader trend in modern geophysical research toward documenting intersystem coupling at large spatial scales. Recent research has identified, for example, simultaneous rupture episodes along the San Andreas Fault in California and the Cascadia subduction zone off the Pacific Northwest, which appear to be coupled through the deeper geometry of the subducted Farallon Plate. Earthquake catalogues from the Pacific Rim show statistical patterns of clustering that are difficult to explain purely by chance, with concentrations of major events in specific multi-year windows separated by quieter intervals. The literature on these patterns is still developing, and consensus on the underlying mechanisms remains elusive, but the empirical signal that something is happening at plate scales is real. There is also a specific case study that is worth bringing in here, which is Kilauea Volcano on the Big Island of Hawaii. Kilauea is currently in its 47th distinct eruptive episode of the ongoing 2024 through 2026 eruption sequence. Episode 47 was imminent as of the recording of this video, with the United States Geological Survey Hawaiian Volcano Observatory reporting that pulse rates between successive episodes have been quickening as the eruption sequence has progressed. Kilauea sits over the Hawaiian hotspot, in the geographic centre of the Pacific Plate, far from any subduction zone. Its eruptive activity is driven by deep mantle plume processes that are dynamically distinct from the arc volcanic processes around the Pacific Rim, and yet Kilauea is also in an elevated state right now, at the same time the Western Pacific Arc Cluster is happening. The Pacific Plate Dynamical Coupling Hypothesis would predict exactly this kind of simultaneity. If the Pacific Plate is in a state of elevated activity broadly, that elevated state could manifest as accelerated arc volcanism at the Ring of Fire margins and as accelerated hotspot volcanism at the plate center simultaneously. The Kilauea Episode 47 acceleration is not by itself evidence for the coupling hypothesis, but it is consistent with the hypothesis. The hypothesis does not require Kilauea to be doing this. The hypothesis just predicts that Kilauea behaving in this way is exactly the kind of thing you would see if the plate scale dynamics had shifted. Against this, however, we have to set the counterexample of Popocatépetl. Popocatépetl is a major stratovolcano in central Mexico, sitting on the North American plate, not on the Pacific Plate. Popocatépetl produced a significant ash eruption in early May 2026, with reports of substantial plume heights and ongoing explosive activity. If the Pacific Plate Dynamical Coupling Hypothesis were the dominant explanation for the May 2026 volcanic state, you would not expect simultaneous significant activity at a non-Pacific Plate volcano like Popocatépetl. The presence of Popocatépetl in the May 2026 volcanic snapshot suggests that whatever is going on it is not exclusively a Pacific Plate phenomenon. Volcanic activity is heterogeneous globally as well as in the Western Pacific, and Popocatépettl's contribution to the May 2026 picture indicates that some of the cluster is just statistical noise across the planetary volcanic system. The honest framing is that the Pacific Plate coupling hypothesis is scientifically interesting, is consistent with a real trend in modern geophysical research, and is the kind of frame that the audience should be able to hold without being asked to commit to it as established fact. It is below the threshold of scientific consensus. It is above the threshold of pure speculation. It is the kind of hypothesis that the next decade of plate-scale geophysics research will probably resolve in one direction or another, and the answer that comes back from that research will be one of the most important answers in 21st century geophysics. For now, what we can say is that the May 2026 Western Pacific cluster is real, that it is unusually intense, that some of its intensity is probably chance, and that some of it may be evidence of plate-scale coupling that has not yet been fully characterized. For the central Bismarck Sea event specifically, the coupling hypothesis adds one specific consideration. If the cluster is partially driven by plate-scale dynamics rather than fully by chance, then the structural conditions that have produced the cluster are conditions that persist at the plate scale, not at the individual volcano scale. The central Bismarck Sea volcano is participating in something larger than its own local geology. The eruption duration, the probability of escalation, the magnitude of the volcanic edifice's elevated risk envelope are all potentially modulated by the broader Pacific Plate state. This does not change the operational interpretation of the immediate event much. It does suggest that the cluster as a whole is worth watching as a coherent phenomenon, not just as 6 separate stories. The Silver et al. 2008 paper noted that larger flank collapse events in the Bismarck Arc tended to be associated with periods of elevated arc-wide volcanic activity, and the May 2026 cluster is precisely the kind of arc-wide activity peak that the Silver paper's statistical association would flag as elevated risk. To bring this back to the central thread, the Western Pacific cluster does not, by itself, increase the probability of a flank collapse at the central Bismarck Sea volcano in any individual day. But it does suggest that the system is operating in a regime where the structural conditions for collapse are more likely to align than they would be in a quieter arc-wide state. The cluster is context, not cause, but the context matters, and the context says, this is not a routine eruption at a routine moment. This is an unusual eruption at an unusually active moment. Both of those facts are real, and both of them belong in the operational picture. Part 13. The frames that are not true. By the time a major volcanic event like the central Bismarck Sea eruption has been visible on satellite imagery for a few days, the conspiracy frames have already taken over a significant fraction of the online discussion. This is a structural feature of how information ecosystems respond to dramatic geophysical events, and it is something we have to engage with directly, because the audience for this video is encountering these frames whether we address them or not. The honest approach is to lay out each of the most common frames, explain what the physics says, and let the audience hold the answer with confidence. The first frame is the one that has the longest pedigree, and that is the frame that the eruption was triggered by deliberate human intervention through geoengineering or weather modification technologies, most often specifically through HAARP or HAARP-class ionospheric heaters. The argument typically asserts that the simultaneity of multiple volcanic events across the Western Pacific, combined with the perceived increase in tectonic activity globally, indicates a coordinated effort to destabilize the lithosphere through electromagnetic forcing applied from above. The energy budget argument decisively rules this out. The total operational power of all known HAARP-class and ionospheric research facilities globally is approximately 3.6 megawatts. The energy released by a single magnitude 5.6 earthquake is approximately 10 to the 11th joules, which is 100 billion joules. The energy required to initiate a magmatic intrusion sufficient to drive the present eruption, accounting for the heat content of the rising magma, the pressure volume work done against the surrounding rock, and the energy required to fracture the lithology and open a conduit, is in the range of 10 to the 17th to 10 to the 19th joules, which is 100 million billion to 10 quintillion joules. The total daily energy output of the global geothermal and tectonic energy budget is on the order of 10 to the 20th joules per day. HARP-class systems are therefore 9 to 15 orders of magnitude too small to initiate, modulate, or trigger any volcanic event of any kind. This is not a matter of insufficient evidence, it is a matter of physical impossibility at the relevant energy scales. The geoengineering trigger interpretation is therefore not a credible alternative. It is not a question of whether HARP could do this and chose not to. It is a question of whether HARP could do this, and the answer is no, by a factor of 10 to the 15th. The second frame is the one that has been more prominent on this channel and others in recent months, and that is the frame that the eruption was triggered by solar forcing, by coronal hole high-speed streams, by capacitive coupling of geomagnetic activity into the lithosphere, or by other mechanisms involving the Sun-Earth connection. The peer-reviewed literature on solar seismic correlations is real. The Marchitelli et al. 2020 paper in Scientific Reports documented a weak, statistically significant correlation between solar activity and global seismicity. The Mizunokao Umeno work out of Kyoto, published in 2026 in IGPEST, proposed a specific capacitive coupling mechanism by which elevated geomagnetic activity could modulate the electrical state of the upper crust and influence the failure behaviour of pre-stressed faults near their failure threshold. The honest framing of this body of research is that it documents a real but weak correlation with mechanisms that remain speculative and contested in the broader seismological community. The correlations identified are weak. The mechanisms proposed have not been independently confirmed. The effects, if they are real, are small modulations of base rate seismicity, rather than primary triggers of major events. And critically, for the present case, the capacitive coupling mechanism requires elevated geomagnetic activity during the trigger window for the effect to be operative. The geomagnetic record for the May 7th and 8th window, immediately preceding the central Bismarck Sea main shock, shows KP values in the 1.67 to 3 range, geomagnetically quiet conditions. There was no Earth-directed coronal mass ejection in the preceding days. The May 10th magnitude 5.7 solar flare from region 4432 was located at N21E65, glancing rather than direct, and occurred after the main shock, not before it. The leading candidate solar seismic mechanism is, for this specific event, decisively absent. The space weather backdrop is actively inconsistent with the solar forcing trigger framing. The honest conclusion is that the solar seismic correlation literature exists, that it documents weak effects with uncertain mechanisms, and that the specific event we're watching is one where the proposed mechanisms are not present. Solar forcing is not a viable trigger explanation for the central Bismarck Sea eruption. This is not a dismissal of the underlying research program, which is legitimate and ongoing. It is a statement that the research program's findings do not apply to this specific event because the prerequisite conditions are not met. The third frame is the concealment frame, which asserts that governments are aware of the elevated tsunami risk and are deliberately concealing warnings to prevent panic. The structural argument against this is straightforward. The Pacific Tsunami Warning Center, the United States Tsunami Warning System operated through NOAA, and the Australian Tsunami Warning System all publish their advisories, warnings, and the underlying observational data in real time to public-facing portals. The structural incentives faced by these institutions run directly opposite to concealment. The failure to warn when a warning is warranted carries career-ending consequences for individuals, legal exposure for institutions, and severe institutional reputation damage that the agencies have no incentive to risk. The current absence of a tsunami warning reflects the current absence of a tsunami signal, not active concealment. The Pacific Tsunami Warning Center is publishing its data. The data shows no tsunami. There is no tsunami to warn about yet. If a tsunami is generated by a flank collapse in the coming days, the warning system will issue advisories as fast as it can, and the operational limitation is the propagation time of the wave relative to the propagation time of the warning to the affected coastlines, not the willingness of the agency to issue the warning. The fourth frame is the supernatural omen frame, which has circulated in folk and religious commentary around volcanic cluster events for as long as humans have observed volcanic activity. The frame typically casts the cluster as a sign, a portent, a message that something larger is shifting. The scientifically defensible interpretation of the cluster, which we covered in Part 12, is that some of it is chance and some of it may reflect plate scale dynamics. Whether the cluster has meaning in the sense the omen framing implies is not a question scientific methodology can address. The audience can hold whatever frame they wish about meaning. What I can say with the tools of geophysics is that the cluster is real, that some of it is unusual, that the underlying mechanisms are matters of active research, and that no version of the available evidence requires or supports the supernatural framing as a causal explanation. The framing is meaningful to those who hold it. The eruptions would happen with or without anyone interpreting them. The fifth frame, which has occasionally circulated specifically around the central Bismarck Sea volcano because of its remote location and the unusual acoustic detection history of its 1972 eruption, is the frame that the 1972 acoustic signal was not actually a volcanic eruption, but a covert underwater nuclear test conducted in the Western Pacific. The argument typically asserts that the location and the timing of the 1972 signal are inconsistent with any catalogued nuclear test, and therefore the signal must have been from a clandestine test that was misattributed to volcanic activity. The Comprehensive Nuclear Test Ban Treaty Organization International Monitoring System, the CTBTO-IMS, was not yet fully operational in 1972, but the seismic and hydroacoustic forensic discriminants that distinguish volcanic eruption signatures from nuclear explosion signatures were well established by the time of the event. Volcanic eruptions produce acoustic signals with characteristic rise times, frequency content distributions, and durations that are distinct from nuclear explosions. Volcanic signals are longer, lower in frequency, and more variable in amplitude than the sharp, impulsive signature of a nuclear test. The 1972 signal that led to the discovery of the central Bismarck Sea volcano matches the volcanic signature, not the nuclear signature, by every available forensic discriminant. The covert nuclear test interpretation is not supported by the acoustic record. It is, like the other conspiracy frames, a frame that exists in some quarters, but that does not survive contact with the actual data. Part 14. Ranking. The 5 hypotheses. What I want to do now is take the 5 interpretive frames we have built up across this video and rank them by physical plausibility and operational relevance. I have already discussed each individually, but bringing them together explicitly is useful, because each frame has different implications for what the audience should be watching for and what the appropriate posture is for coastal populations in the affected region. Hypothesis 1 is the routine submarine arc eruption interpretation. Under this reading, the central Bismarck Sea event is a fairly normal submarine arc volcanism event. A magma intrusion generated the M5.6 main shock. The intrusion opened a vent. The vent has been producing a sustained ash plume for several days. The eruption will continue at roughly its current scale for some period of weeks. The magma supply will then deplete. The eruption will taper, and the volcano will return to dormancy for an unknown duration that could be decades, centuries, or millennia. This is the modal outcome for submarine arc eruptions of this character. It is the outcome most submarine eruptions historically have produced. The probability assigned to this outcome, given the limited information available, is something like 60 to 70%. Most likely this is what we are watching. Hypothesis 2 is the Hunga Tonga class escalation interpretation. The structural prerequisites that distinguished Hunga Tonga from other submarine eruptions are present in the current event, with the qualifications discussed in Part 10. The probability of escalation to a Hunga Tonga class paroxysm is low. Quantitatively, low, single-digit % over the duration of the present eruption, probably 1 to 3%. This is not a prediction. It is a base rate estimate informed by the rarity of paroxysmal escalation in the historical record. The probability is low, the bound is real. If this hypothesis materializes, the consequences are catastrophic on a Pacific Basin scale. Hypothesis 3 is the flank collapse-generated tsunami interpretation. The structural conditions for elevated flank collapse risk are present, as we documented in Part 7 through 9. The eruption is sustained, the earthquake swarm is ongoing, the ridge geometry is poorly mapped but extends across distances suggesting multi-vent geometry. The historical record from the Silva et al. 2008 paper documents that the Bismarck arc produces flank collapse events on average return intervals around 4,000 years per location, with the 1888 Ritter event being the most recent. The probability of a flank collapse event at the central Bismarck Sea during the present eruption is low in absolute terms, but elevated above the baseline that would apply to the same volcano in a quiescent state. Quantitatively, probably in the low single-digit % over the duration of the eruption. maybe 1 to 5%. The consequences, if this hypothesis materializes, are catastrophic at the regional Pacific scale, with potential immediate casualties on adjacent inhabited coastlines and propagation of destructive waves across hundreds of kilometers. This is the highest impact hypothesis for which the conditions are most clearly elevated, and it is therefore the primary operational concern. Hypothesis 4 is the Pacific Plate dynamical coupling interpretation. Hypothesis is consistent with the May 2026 volcanic cluster, but is not required by it. The plausibility of the hypothesis, in light of the broader trend in geophysics research toward inter-system coupling at large scales, is meaningfully non-zero. The hypothesis does not directly affect the operational probability of any specific outcome at the central Bismarck Sea, but it provides a context in which the cluster as a whole should be watched as a coherent phenomenon rather than as 6 separate events. The probability that the cluster reflects real plate-scale coupling rather than pure chance is uncertain, with estimates ranging widely across the geophysics literature. For the audience, the hypothesis is most relevant as a frame for how to interpret what is happening across the Western Pacific, not as a specific operational guide. Hypothesis 5 is the multi-vent fissure activation interpretation. The structural conditions for this hypothesis are present in the spatial distribution of the earthquake swarm. The interpretation extends the elevated risk window from a few weeks to potentially months or longer if it materializes. The probability that the current eruption is the first in a multi-vent sequence rather than a single-vent isolated event is meaningfully non-zero, with the swarm geometry suggesting it as one of 2 roughly equally plausible interpretations. If the hypothesis is correct, the operational implication is that the elevated tsunami risk window extends well beyond the duration of the current visible eruption into a longer activation phase that could produce additional eruption points and an extended period of edifice instability. The combined most defensible reading, which I argued for in the source document discussion that informed this script, is that the central event is most likely a combination of hypotheses 1 and 3. The eruption itself is most likely a routine submarine arc event that will run its course at roughly its current scale and then end. The elevated tsunami risk is real and meaningfully above baseline, driven by the structural conditions of the eruption, the ongoing seismicity, and the documented arc history. The Hunga Tonga ceiling is real and bounded, but unlikely. The Pacific Plate coupling and the multi-vent activation are both worth watching as secondary frames, but neither is the primary operational concern for any specific decision-making horizon over the next several weeks. What this means for the audience is that the appropriate posture is informed attention, not panic, not dismissal. The eruption is real. The risks are real and elevated above baseline. The most likely outcome is that nothing catastrophic happens at the central Bismarck Sea over the next several weeks, and the eruption tapers off and the system returns to dormancy. The less likely but operationally significant outcomes, the flank collapse tsunami, the multi-vent activation, the proximal escalation, are low probability outcomes whose low probability is exactly what makes them appropriate to keep watching for rather than to assume away. For coastal populations in the affected region, the appropriate posture is awareness, preparedness, and attention to local guidance from the Papua New Guinea National Disaster Center and the Pacific Tsunami Warning Center. The eruption itself does not require immediate evacuation. The downstream events that would require immediate response are those for which the warning architecture cannot reliably provide advance notice. As we discussed in Part 9, knowing what to do if a tsunami warning is issued, knowing the routes to higher ground, knowing the local terrain in the way that coastal populations of historically tsunami-affected regions have always needed to know it, is the practical operational response to the current situation. It is what the eruption is asking of the affected coastlines. Part 15. What to watch. We are coming to the end of this video, and what I want to do in the final part is leave you with a specific framework for what to watch over the coming days and weeks, so that whatever happens next at the central Bismarck Sea volcano, you have the conceptual structure to interpret the new information as it arrives. The first watch window is the next 48 to 72 hours. The 2 most diagnostic signals during this window are the seismic catalogue and the satellite imagery. On the seismic side, the question is whether the magnitude floor of the catalogue continues to climb, holds steady, or declines. A catalogue showing the largest event remaining the May 8th magnitude 5.6 is most consistent, with a single large intrusion that is now bleeding off, with the eruption proceeding to its eventual taper. A catalogue showing new events at magnitude 5.5 or above over the coming days indicates fresh magma is continuing to arrive, that pressure is building rather than releasing, that the eruption may still be in an early phase. A catalogue showing the largest events declining toward magnitude 4 and below indicates the system is transitioning toward the post-eruption phase. On the satellite imagery side, the question is whether the ash plume sustains its current altitude and density, increases or decreases. The plume is the visible heartbeat of the eruption. As long as the plume is climbing to 9,000 feet and the spread is reaching 40 kilometers, the eruption is sustained at its current intensity. The second watch window is the next 1 week. During this window, what to watch for is the appearance of any signs that the multi-vent activation hypothesis is materializing. The diagnostic signal is the appearance of new ash plumes from secondary locations along the central Bismarck Sea ridge, separated by kilometers from the current primary vent. New plumes would show up on satellite imagery as discrete additional eruption points, potentially preceded by localized earthquake swarms at the new vent locations, with magnitudes in the 4 to 5 range. The probability that the multi-vent hypothesis materializes within the first week is uncertain, but meaningfully above zero. If new vents appear, the elevated risk window extends substantially beyond the duration of the current eruption. The third watch window is the next several weeks to month or two. Over this longer window, the question is whether the eruption tapers in the way most submarine arc eruptions historically have, or whether it sustains at its current scale or escalates. A taper would manifest as gradual decline in ash plume altitude and density over the course of weeks, accompanying decline in seismic activity, eventual disappearance of the visible signature from satellite imagery. Sustaining or escalating would manifest as continued plume activity at current or higher intensity, continued seismic activity, potentially the development of new vents, potentially the emergence of new structural signals from the edifice. The longer the eruption sustains, the more time the system has to develop the kind of structural stress that could precipitate a flank collapse event. Time is, in this case, not necessarily on the side of the volcanic edifice. Throughout all 3 watch windows, the highest impact signal to watch for is any disturbance at coastal tide gauges in the Bismarck Sea or adjacent waters. Coastal tide gauge data is freely available, in many cases in near real time, through national tide gauge networks operated by the relevant geophysical agencies. Any unusual signal at gauges on Manus Island, on New Britain, on the islands of the southern Bismarck Arc, or on the broader Papua New Guinea coast would be the diagnostic signal that a tsunami has been generated. The warning architecture would, in such an event, issue regional warnings as fast as it could, but the gauge signal would be the first indication that the downstream catastrophic event has occurred. As of the recording of this video, no such signal has appeared. The hope, and the most likely outcome, is that no such signal will appear over the coming weeks. The watch is for the small probability that one does. Beyond the immediate operational watch, there are larger questions this event raises that I want to leave the audience with, because they are questions that this story is going to keep returning to over the coming months and years, regardless of how the immediate event resolves. The first question is what the May 2026 Western Pacific Volcanic Cluster is going to look like in retrospect 6 months from now, 12 months from now, 5 years from now. If the cluster represents a coherent plate-scale phenomenon rather than pure chance, then the eruptions we are watching now are the early manifestations of something that will continue to unfold across the broader Pacific Basin over the coming years. The Sakurajima pyroclastic flow, the Mayon ongoing PDC activity, the Dukono tropopause reaching plume, the Lower Toby Laki Laki escalation, the Central Bismarck Sea event, the Kilauea episode 47 acceleration at the hotspot center, all of these would be parts of a larger pattern that we are seeing through a partial window. The question of whether the next 18 months will see continued elevated arc-wide and hotspot volcanism in the Pacific is an open question whose answer will tell us a lot about whether the coupling hypothesis is real. The second question is what we're going to learn about the central Bismarck Sea ridge as a result of this event. The eruption has put a previously obscure submarine volcanic system on the global volcanological map. The post-eruption surveys, the bathymetric mapping that will be conducted by research vessels in the coming months, the geochemical sampling of the erupted material, if it can be recovered from surface pumice rafts, or from sediment cores, will give us a detailed picture of a system we have spent 54 years not looking at. The scientific output from the central Bismarck Sea ridge over the coming year is going to be substantial, and our understanding of submarine arc volcanism at this kind of depth and this kind of fissure geometry will advance as a result. The third question is the deeper one, the one that I keep coming back to in everything we do on this channel, which is the question of how interconnected the planet's geophysical systems actually are. The traditional approach in geophysics has been to treat individual systems as relatively isolated, with the assumption that the dynamics at one location are largely independent from the dynamics at another location far away. The newer trend in research, in the simultaneous rupture documentation along the San Andreas and Cascadia, in the studies of teleseismic triggering, in the work on plate-scale stress redistributions, is increasingly suggesting that the planet is more coupled than we have historically treated it. The central Bismarck Sea event, in the context of the Western Pacific Cluster, in the context of the Kilauea acceleration, is one more data point in an accumulating dataset that suggests we have been underestimating the connectivity. If the connectivity is real, the implications for how we forecast and prepare for major geophysical events are substantial. We have to start treating the planet as a coupled system, with the events at one location informing the probability of events at distant locations through mechanisms we have only begun to characterize. For now, the central Bismarck Sea is erupting, the ash plume is climbing, the earthquake swarm is rolling through, the 1888 Ritter Island flank collapse debris fan is at the bottom of the Bismarck Sea 200 kilometers south, holding the memory of what this kind of system can do at its worst. The Hunga Tonga eruption of January 2022 is in the recent memory of everyone who has paid attention to volcanism in the Western Pacific, holding the memory of what an underwater eruption can become at its absolute upper limit. The 1,600 dead at Aitape are in the memory of the Papua New Guinea coastlines, holding the warning that warning systems cannot always warn, and the volcano itself, the central Bismarck Sea volcano, the one that we forgot for 54 years, has come back. It is a poorly understood system erupting through a mile of water in a part of the world where we have spent decades not looking, and the question that the next several weeks are going to answer, in one direction or another, is whether it stays at the scale it is at right now, or whether it does something we have to remember for the next century. I will be watching. I hope you will be too. We will be back tomorrow night with whatever the next 24 hours brings. Until then, take care of yourselves, take care of the people you love, and pay attention to the world that is moving underneath you, because it is moving more right now than it usually does.